The seabed off England's south coast, from the Solent out toward the approaches of the English Channel, is littered with legacy military debris and the lingering risk of unexploded ordnance. Before laying a major infrastructure link, engineers must scan the designated route for hazards. During a routine unexploded ordnance survey for the high-voltage subsea power cable known as Interconnection France, Angleterre 2, IFA2, sensors detected a large metallic anomaly. The planned route required a clear path for the subsea link connecting two national power grids. Remotely operated vehicles and divers were deployed to inspect the target, expecting to find standard wartime scrap or an unexploded mine. Instead, they found the wreckage of a military aircraft resting in the silt. The target was identified as a Fairey Barracuda Mark II. The Barracuda is widely described as the Fleet Air Arm's first all-metal monoplane torpedo bomber, later used across multiple attack roles. During the Second World War, more than 2,500 Barracudas were delivered to the Fleet Air Arm from a wartime production run that exceeded that figure. Despite that massive output, no complete Barracuda survives intact today. What survives in museums is a patchwork of fragments and careful reconstruction. Finding a substantially preserved airframe on the designated cable route created an immediate operational conflict and stopped the cable schedule cold. Project managers faced a direct geographical intersection between historical preservation and modern energy infrastructure. The aircraft sat exactly where the main electrical conduit needed to go. The initial proposal to bypass the wreck by altering the cable route was quickly rejected. The decision was not based on legal boundaries, but on rigid physical limitations. High-voltage direct current subsea cables cannot be routed with tight, abrupt turns because the cable system has a minimum bend radius driven by mechanical stress and insulation integrity. Force the route to kink, and you risk damaging the protective layers, deforming the cable's structure, and compromising the electrical insulation that must remain continuous under load for decades. The engineering specifications for the roughly 127-mile line demanded gradual curves, controlled tension during installation, and a precisely graded seabed. Bypassing a localized obstacle like an aircraft wreck would require a detour with curvature beyond the allowable bend radius for the installed cable system. There was no workable detour. The wreck had to move. Leaving the aircraft undisturbed would have broken the link at its most critical point. Clear the corridor or the link fails. This mandate shifted the operation from a standard hazard clearance task into a highly complex salvage mission. Any recovery would unfold under strict oversight, far beyond a normal clearance job. The unexploded ordnance survey teams had already plotted hundreds of minor targets across the coastal shelf. Most of these targets were easily bypassed or safely detonated in place. This one target rewrote the playbook. The Ministry of Defense had to be notified, and any interference with the wreck, disturbing, or moving, recovering, or removing material required the appropriate license under the Protection of Military Remains Act before work could proceed. The recovery teams realized they were not just dealing with scrap metal, but with an irreplaceable source of original structural data. If they simply dragged the wreckage out of the path, they would destroy the only known source for several internal mechanical components. The operation required a delicate touch in an industrial environment. The project engineers had to design a recovery plan that satisfied both the utility operators who needed the corridor cleared and the heritage authorities who required the artifact preserved. Every step forward was dictated by the unyielding geometry of the power cable route. The utility company provided the necessary funding and logistical support to extract the aircraft, knowing it was the only way to finalize their high-voltage connection. The engineering standoff was resolved, but the physical reality of the extraction remained completely undefined. With the route locked, the question was no longer whether they would move it, but how it had ended up here in the first place. An engine failure immediately after takeoff traps a pilot in a brutal, non-negotiable choice. Contemporary records and later research indicate that a Barracuda Mark II ditched in this coastal sector after an engine problem shortly after launching from Royal Naval Air Station Lee-on-Solent. Low, slow, and heavily laden over the south coast water, for the crew could not risk a turnback at knife-edge height, so they went straight ahead and put it into the sea. In that moment, survival outranks the airframe. executing a water landing in a 5-ton bomber requires precise energy management. Water creates severe hydraulic resistance when struck at high velocity. The pilot must decelerate the aircraft to the absolute minimum flying speed before contacting the surface. This controlled ditching dynamic dictates bleeding off airspeed to intentionally stall the wing just inches above the water. By exchanging the last remaining knots of forward velocity for a flat horizontal attitude, the pilot minimizes the total kinetic energy transferred to the airframe upon impact. A high-speed plunge would shatter the fuselage and destroy the cockpit, but managing the deceleration preserves the structural envelope. The pilot survived the crash, and records report no fatalities, proving the effectiveness of this disciplined procedural trade-off. The wreck itself backed that story, down to details too fragile to survive a hard hit. When marine archaeologists first surveyed the site decades later, one fragile detail stood out. The underwing pitot tube, mounted on a thin bracket, was still intact and still attached. In a high-speed impact, that kind of delicate hardware is usually the first thing to go. After the crew evacuated, the metal airframe filled with water and descended to the sea floor. Because the impact was managed, the aircraft did not shatter into a scattered debris field. Instead, it sank largely whole and came to rest on the coastal shelf. The specific geology of the Solent seabed played a crucial role in the preservation of the wreckage. The bomber settled onto a dense layer of heavy marine clay. This compacted clay barrier acted as a hard stop, preventing the weight of the engine block and fuselage from driving the aircraft entirely into the subsoil. While the structure did not vanish completely into the seabed, it did not remain exposed. Over the next 75 years, tidal currents blanketed the aircraft in a thick layer of soft silt. The coastal marine environment is hostile to manufactured aluminum. Prolonged exposure to saltwater initiates galvanic corrosion, steadily weakening the factory rivets, internal spars, and load-bearing frames. The silt overburden completely obscured the visual profile of the bomber, masking its location from passing vessels, while the internal strength degraded. The aircraft became an artificial reef, deeply integrated into the marine ecosystem. Decades later, its buried outline returned as an unexpected obstruction to a modern high-voltage link. Locating a buried metal object in a tidal channel is only the first step of a forensic salvage operation. The shallow site conditions that buried the bomber also created a severe technical barrier for the engineering teams attempting to map it. Decades in coastal silt meant accessing the wreck required navigating an environment hostile to modern underwater tracking sensors. Operating in coastal margins introduces severe sensor limitations. The targeted anomaly rested just 1,600 feet off the shoreline. The water depth at this specific coordinate was a mere 16 feet. While extremely shallow water allows for longer diver bottom times without complex decompression schedules, it can complicate standard underwater navigation systems. The unexploded ordnance survey teams initially approached the target expecting to find a magnetic mine or a discarded torpedo. Their first priority was hazard identification, which requires positional accuracy to establish a safe exclusion zone. When the divers deployed to investigate the metallic signature, their topside tracking became noisy and unstable. Not because acoustic positioning is impossible here, but because the shallow geometry turns each ping into a tangle of echoes. To track a diver or a remotely operated vehicle, support vessels rely on acoustic beacons that transmit sound pulses to a receiver. In deeper water, those pulses travel in a clean, direct line. In water, this shallow, reflected returns can arrive close behind the direct signal. The topside receiver may pick up the true pulse alongside secondary echoes, and the software must work harder to separate the primary return from the reflections. With careful setup and the right tools, teams can still maintain usable acoustic positioning. But it is an unforgiving environment. Without relying on a single stream of coordinates alone, the archaeological team strengthened their mapping with high-resolution optical modeling. The recovery team deployed a specialized imaging system to perform real-time photogrammetry. Instead of plotting only point positions, the high-definition cameras captured continuous stereoscopic video of the seabed. As divers carefully cleared away the silt overburden, the optical system recorded every newly exposed mechanical component. Advanced software processed the visual feed instantly, stitching thousands of individual optical frames together to build a three-dimensional digital twin of the site. Because the imaging system updated dynamically during the excavation, the engineers topside could monitor the progressive uncovering of the aluminum structure in real time. This optical methodology completely neutralized the signal bounce confusion caused by the extreme shallow depth. The Solent is characterized by strong tidal currents that constantly shift the soft seabed materials. And visibility can drop to 0 in seconds if a diver disturbs the wrong pocket of fine clay, so the continuous capture mattered as much as the model itself. Even when the water clouded over, the team already had survey-grade scale and geometry locked in place, detail limited only by clarity, range, and camera angles. It let engineers assess corrosion and deformation without putting hands on metal that could crumble under the lightest touch. The survey transformed a buried, invisible hazard into a fully quantified engineering schematic. The utility company now had precise dimensions of the obstacle blocking their high-voltage corridor, while the heritage authorities had a permanent forensic record of the wreckage in its undisturbed context. The optical map revealed the full extent of the structural decay caused by decades of saltwater immersion. The airframe still held its overall layout, but its load-bearing strength was gone. With the site fully mapped through the silt, the team faced the critical engineering problem of physically detaching the wreck from the sea floor. Trying to raise a 5-ton military bomber in a single lift would tear it apart. After more than 7 decades in saltwater, corrosion had erased the strength that the map still seemed to promise. What looked intact in the model was, in structural terms, no longer load-bearing. The recovery team faced a rigid mechanical trade-off. If they attached crane slings directly around the main fuselage and executed a standard whole airframe extraction, the upward pull of the winch would fight against the massive drag of the water. This opposing force creates severe shear stress across the weakest points of the corroded airframe. The most dangerous phase of any marine salvage is the transition through the surface. The moment the aircraft breaks the waterline, it instantly loses the supportive force of buoyancy. The effective weight of the metal multiplies immediately. Under those forces, the wing roots would snap, and the fuselage would buckle, scattering irreplaceable wreckage back into the path of the utility corridor. To prevent this structural failure, the engineering team discarded the single-point lift strategy. Instead, they opted for a disciplined sectional recovery. The goal was to separate the wreck into manageable units while protecting what remained of the corroded structure. Marine archaeologists and salvage engineers developed a separation plan that respected major structural breaks and attachment zones, using careful handwork and, where corrosion had fused components together, controlled cutting, to free sections without tearing the weakened airframe apart. Divers deployed to the seabed to locate the primary junctions connecting the wing sections, the tail assembly, and the main cockpit block. By carefully separating the aircraft into distinct, isolated pieces, the team reduced the risk of dynamic shear loads ripping through the weakened structure during the hoist. Once a section was successfully detached from the main body, it was gently manipulated through the water column and secured inside massive subsea lifting baskets that had been lowered to the seabed. The mechanical logic of this sectional lift relies entirely on transferring the load path. By securing the fragile aviation components inside rigid industrial steel cages, the destructive mechanical strain of the crane hoist is bypassed entirely. The heavy steel rigging of the basket absorbs 100% of the lifting force. The delicate aircraft components simply ride inside the basket as completely passive cargo. Inside the basket, the aircraft rides as passive cargo, spared the crush of slings, and the hard moment it meets open air. Executing this methodical underwater deconstruction required absolute procedural discipline from the dive team. Operating in an environment dominated by shifting tidal currents, the divers had to handle heavy hydraulic tools next to fragile historical evidence without causing collateral damage. The complete salvage sequence, from the first careful separations on the seabed to the final crane hoist onto the deck of the support barge, consumed around 3 weeks of sustained operational effort. This intensive operation was the only viable method to permanently resolve the bend radius constraint that had paralyzed the infrastructure project. The utility company required a completely empty channel to lay their heavy power lines. As the final subsea basket touched down precisely on the wooden staging mats of the recovery barge, the primary objective was fully realized. The seabed corridor was finally clear. The fragile sections were safely secured on the recovery barge, but historians quickly realized the physical evidence did not match the official records of the crash. When a submerged aircraft is brought to the surface, the physical evidence rarely aligns perfectly with the initial historical assumptions. Before the first metal components were even hoisted from the sea floor, archival researchers had tentatively identified the bomber based on local loss records. The prevailing consensus pointed to a Blackburn-built airframe carrying the designation BV739. For the initial phase of the clearance project, all official documentation and engineering briefings operated under the strict premise that the target was this exact Blackburn machine. However, as conservation experts began systematically washing away the dense layers of marine clay on the deck of the recovery barge, unexpected hardware details started to emerge. The team faced a classic forensic discrepancy between the written historical timeline and the tangible mechanical artifact. On a wreck this degraded, the truth isn't on the outside. Standard visual markers like squadron identification codes, painted tail numbers, and exterior camouflage patterns are immediately destroyed by 75 years of aggressive saltwater immersion. To establish an undeniable chain of evidence, researchers must rely on completely internal components that remained perfectly sealed against the marine environment. The Barracuda was an intricately designed machine, and to meet immense wartime operational demands, the British government decentralized its production. While Fairey Aviation originally designed the bomber, the actual manufacturing burden was split across several different heavy industrial contractors, prominently including Blackburn Aircraft. These completely separate assembly lines built aerodynamically identical airframes from the exact same engineering blueprints. This parallel manufacturing process meant the raw aluminum ribs, spars, and brackets were visually indistinguishable from one another. To determine whether the recovered wreckage came from a Fairey-built machine or a Blackburn-built machine, the investigative team looked beyond shape and hardware and into the chemistry of what the factories left behind. During wartime manufacturing, different plants could draw protective coatings from different suppliers, and internal primer layers sometimes retained identifiable chemical characteristics. If the conservation team could isolate surviving primer, trapped deep inside protected joints and internal bulkheads, they could compare it against known manufacturing patterns. Basic visual inspection under a microscope cannot determine elemental makeup, especially when the material is contaminated by decades of marine biology and silt. The conservation engineers subjected carefully extracted internal paint samples to spectroscopic analysis, including X-ray fluorescence and Fourier transform infrared methods. Those tests produced a compositional profile consistent with Fairey production practices and inconsistent with the attribution that had guided the early paperwork. The material evidence strongly ruled out Blackburn Aircraft as the manufacturer of the submerged bomber. Alongside corroborating mechanical indicators recovered from the wreckage, the balance of evidence is most consistent with the aircraft being LS-473, while acknowledging that some uncertainty can remain when historical loss records and underwater site data are incomplete. With the identity clarified to the strongest supported conclusion, the recovered components could finally fulfill a role no other artifacts in the world could provide. Extracting around 60 to 65% of a heavily degraded military aircraft from an active tidal zone represents a highly successful marine salvage yield. When the recovery operation officially concluded, the power link could proceed, and maritime historians held a massive influx of irreplaceable aviation hardware. The remaining material was not recovered, whether because it had already broken away before the project began, lay too deeply embedded, or lacked the structural integrity to survive safe handling. Despite these losses, the sections that were successfully hoisted onto the barge were precisely the components that modern preservationists required most. The salvaged wreckage was transported from the coastal staging area directly to the conservation facilities at the Fleet Air Arm Museum. For decades, the museum had been pursuing a full-scale reconstruction of the bomber. Because no intact Barracuda exists anywhere, the team had to combine recovered fragments with newly fabricated structure. But the project kept hitting the same hard limit. The most intricate internal parts, control linkages, stamped brackets, molded fittings, were never fully captured in surviving drawings. Without original jigs or complete schematics, The only reliable path was an exact three-dimensional physical template to verify dimensions, bend radiuses, and attachment angles. The wreckage recovered from the coastal shelf perfectly provided that missing physical data, because the lower half of the aircraft had settled firmly into a protective layer of dense marine clay. Dozens of these rare, uniquely molded parts survived the corrosive environment in a geometrically intact state. The conservation team immediately initiated a rigorous stabilization protocol for these newly recovered sections. They systematically washed away the corrosive chloride salts in specialized freshwater baths and carefully applied chemical corrosion inhibitors to halt any further degradation of the fragile aluminum. Once properly stabilized and environmentally neutralized, these mechanical artifacts were meticulously cataloged and directly integrated into the ongoing restoration project. The engineering technicians could finally replicate the missing control column assemblies, the wingfold mechanisms, and the internal cockpit frameworks by physically measuring the heavily corroded but dimensionally accurate originals. Furthermore, the absolute certainty provided by the chemical manufacturer signature meant the museum team knew exactly which specific wartime production block they were evaluating. This forensic clarity allowed the engineers to confidently match the newly recovered aircraft parts with the correct corresponding technical manuals. There was no longer any technical ambiguity regarding the specific origin or the baseline mechanical tolerances of the salvaged hardware. Every factory rivet pattern, every internal bulkhead measurement, and every load-bearing spar alignment extracted from the recovered wreckage directly advanced the structural accuracy of the rebuild effort. What began as an unavoidable infrastructural clearance mandate ended as a vital heritage acquisition. The strict engineering requirement to clear a utility corridor inadvertently accelerated a massive leap forward for aviation archaeology. The disciplined partial recovery of this completely compromised airframe permanently closed a critical supply gap for the preservation team. By physically extracting the weakened structure before it completely collapsed into the seabed, the recovery operation ensured that the exact physical dimensions of a highly complex bomber were finally secured. The definitive, measurable legacy of this salvage mission is the direct physical integration of these once-lost components into the only fully reconstructed airframe in the world.